Hi everyone, my name is Christine. I'm a second year at Wayne State University and I am studying biomedical engineering. For my tutoring video, I have chose the course MAT 2150, which is Differential Equations. And when I took this course, I took it with instructor Luca Candelori. In this video, we are focusing on first-order differential equations. There are many different types of these first-order equations, such as separable, linear, exact, special integrating factors, substitutions and transformations, and Bernoulli equations. For the purpose of this video, we are focusing on the first three. So let's get started. The first type is separable equations. How do we solve these? Well, step 1 is to separate the variables. Step 2 is to take the integral of both sides. And step 3 is to simplify and solve for the solution. Let's take an example. I have chosen this equation, x times dy over dx is equal to 1 over y cubed. As you can see, this equation can be separable because you can get y on one side and x's on the other. And this equation is first order since the derivative is in first order because dy doesn't have a prime on it or anything. So going on to the steps, step 1 is to separate the variables. What I did is that I multiplied y cubed to the left side and I divided x and multiplied dx to the other side. That results in y cubed dy is equal to 1 over x dx. Step 2 is to take the integral of both sides, and that would result in the solution, which is y to the fourth over 4 is equal to the natural log of x plus c. This is an implicit general solution. And a general solution is when there's a c and we don't know the value for it, and there's no initial value to solve for it. However, if you're asked for the explicit general solution, we'd have to get y by itself. To do so, I multiplied 4 and I took the fourth root of the right side. This would be your explicit general solution, and as said before, general solution is where there's a c and explicit is where the y is alone. The next type of equations that we're looking at are linear equations. To solve these, we would have to first rewrite in standard form. Standard form of linear equations is dy over dx plus p of x times y is equal to q of x. The second step is to calculate for the integrating factor, which is I of x. Step 3 is to plug into the equation below, which is y equals 1 over I of x times the integral of I of x times q of x dx. Step 4 is to simplify and solve for the solution. Let's take a look at this example. I have chose the equation dy over dx is equal to y over x plus 2x plus 1. As you can see, this isn't separable since there are addition of 2x and we cannot separate the y from it. So we would have to look at linear equations, and this is first order since dy over dx is the first derivative. So following the steps, we had to rewrite in standard form. So to do so, I just subtracted y over x to look like this. dy over dx minus y over x is equal to 2x plus 1. To make it easier to pick out the p of x and q of x, I've rewritten the equation as this. dy over dx minus 1 over x times y is equal to 2x plus 1. Now it's super easy to see where p of x is and where q of x is considering the standard form. So p of x is equal to negative 1 over x, and q of x is equal to 2x plus 1. Second step is to calculate for the integrating factor. So I of x is equal to e raised to the integral of p of x times dx. So I plugged in p of x into the equation that I have given. So I of x is equal to e raised to the integral of negative 1 over x times dx. Solving for the integral and simplifying, we would get I of x is equal to 1 over x. Now we have all three variables of p of x, q of x, and I of x. Next, all we have to do is plug into this equation. The equation is y equals 1 over I of x times the integral of I of x times q of x times dx. Plugging in all those variables, we would get y equals to 1 over x times the integral of 1 over x times 2x plus 1 dx. I simplified this equation, so 1 over x turns into x, and I distributed 1 over x to 2x plus 1, and that equals 2 plus 1 over x inside the integral. Now I solved for the integral, and that results in y equals x times 2x plus the natural log of x plus c. Now this is your explicit general solution, and as stated before, explicit is where y is standalone, and this is a general solution because we do not have an initial value to solve for c. All right, we're gonna do another example with linear equations. So for this example, I've chosen dy over dx plus 3y over x plus 2 is equal to 3x. Following the steps that I have listed, we first have to rewrite in standard form. So what I did was I subtracted the 2 on both sides, so the result is dy over dx plus 3y over x is equal to 3x minus 2. Now to make it easier to pick out p of x and q of x, I've rewritten it as dy over dx plus 3 over x times y is equal to 3x minus 2. From there, we can easily pick out that p of x is equal to 3 over x, and q of x is equal to 3x minus 2. The next step is to calculate the integrating factor. So again, I of x is equal to e raised to the integral of p of x dx. I plugged in p of x, which is 3 over x, and simplifying and solving, we would get I of x is equal to x cubed. Next, we have to plug into this equation. The equation again is y equals 1 over I of x times the integral of I of x times q of x times dx. Plug in I of x and q of x, we would have y equals 1 over x cubed times the integral of x cubed times 3x minus 2. I have further simplified the equation in the integral to be, so then it will result in y equals 1 over x cubed times the integral of 3x to the fourth minus 2x to the third dx. Solving the integral, we would have y equals 1 over x cubed times 3x to the fifth over 5 minus x to the fourth over 2 plus c. Now, this is our explicit general solution, and as I have many times said this, explicit is when the y is alone, and it's a general solution since there's no initial value and there's a constant c. The next type of equations is exact equations. How do we solve these types? Well, step 1 is to rewrite in standard form. The standard form is m dx plus n dy is equal to 0. The second step is to see if the equation is exact. Step 3 is to set phi equal to the integral of m. Step 4 is to take the differential of phi in terms of y and set that equal to n. Step 5 is to find c of y. Step 6 is to plug in and set phi equal to c. Now this may look confusing at first, but after we walk through the example, you guys will understand this for sure. So I've chosen this example. 2xy plus 3 times dx plus x squared minus 1 times dy is equal to 0. Well, since this is already written in standard form, we can easily pull out the m and n from it. So m is equal to 2xy plus 3, and n is equal to x squared minus 1. On your next exam or quiz that you're given, or worksheet, I would be cautious of pulling out your m and n's because the professor could rewrite the equation where dy could be first and then plus dx instead of the other way around as I've written in this example. So I'll just be cautious and make sure that m correlates with dx and n is correlating with dy. Moving on, step 2 is to check if the equation is exact. So what I've written here is that if the differential of m in terms of y is equal to the differential of n in terms of x are equal, then the equation is exact. So let's apply that to this example. The differential of m in terms of y would be 2 of x, and the differential of n over x is also 2 of x. So these are equal, so this equation is exact. If it's exact, we can move on to my steps, and if it wasn't, then we'd have to solve it a different way. So going on to step 3, we set phi equal to the integral of m. Then we would have to solve and plug in m. So phi is equal to the integral of 2xy plus 3 dx. Solving that integral, we would get phi is equal to x squared y plus 3x plus c of y. Next, we take the differential of phi in terms of y. So the differential of phi over y would equal to x squared plus c prime of y. And we would set that all equal to n. So we'd plug in the original n equation, which is x squared minus 1. So then we set x squared plus c prime of y equal to x squared minus 1. So we can obviously subtract x squared from both sides and solve for c prime of y, which equals to negative 1. And for step 5, we have to find c of y. And how do we find c of y when we are given c prime of y? We just have to take the integral of both sides. So solving for the integral, c of y is equal to negative y. As stated before, we solved that phi is equal to x squared y plus 3x plus c of y. All you have to do now is plug in c of y into phi. So phi is equal to x squared y plus 3x minus y. Now we set phi equal to c, and that would equal c equals x squared y plus 3x minus y. Now this is your implicit general solution, since y isn't alone, and it's general because there's still a c, a constant. Alright, since there are many steps to doing exact equations, let's solidify your skills by doing another example. The example that I've chosen is 2x plus y times dx plus x minus 2y times dy equals 0. Again, this equation is already written in standard form where m is and n are easily picked out. So m is 2x plus y and n is equal to x minus 2y. To check to see if the equation is exact, again, you have to take the differential of m in terms of y and the differential of n in terms of x and compare if the values are the same. If they are equal, then the equation is exact. If they are not, then you have to find another way to solve the equation without using these steps. Moving on. So the differential of m is equal to 1 and the differential of n is equal to 1. They are equal, so this equation is exact and we can keep going. So step 3 is to set phi equal to the integral of m dx. So plugging in m, we get phi equals the integral of 2x plus y dx. Solve that integral and we would end up with phi equaling to x squared plus xy plus c of y. Next, we have to take the differential of phi in terms of y and set that equal to n. Solving for that differential, we get x plus c prime of y equal to n. And remember, n is equal to x minus 2y. So setting the differential of phi and n together would equal x plus c prime of y equal to x minus 2y. Now we have to get c prime of y, and all I did was that I subtracted the x's out, and we're left with c prime of y is equal to negative 2y. To find c of y and not the prime, we have to integrate it. So taking the integral of both sides, we will get c of y is equal to negative y squared. Remember, our phi equation is equal to x squared plus xy plus c of y. So now we can just plug in our c of y value, which is negative y squared. And that results in phi equaling to x squared plus xy minus y squared. Our next step is to plug in and set phi equal to c. Now, c is equal to x squared plus xy minus y squared. This is your implicit general solution because the y is not alone and there is still a constant. Thank you so much for listening to this tutoring video, and I wish you the best of luck with your differential equations course with whoever instructor you're taking it with. These types of equations will most likely be on your first exam since this is the first unit, and I would get all these down knowing all the steps of how to solve all these equations because um, the course just builds off of how you solve all these equations. And after this, you would be moving on to second order differential equations, I'm pretty sure. Well, thank you and good luck.